Continuity of functions. What I'd like to do first is I'd like you to read the paragraph at the top. So go ahead and press pause so that you may read the little introduction, please. So after reading the introduction, we're now going to look at a mathematical example of the meaning of continuity. So we have this function graphed in front of us. We have the actual equations on the left and the graph on the right. So let's look at question number 1. Over the interval from -1 to 5, where is the function f discontinuous? So I'm just going to read the graph from left to right, and I'm going to identify each x value where there is a discontinuity. That's where there's going to be a hole or a jump or a gap or somewhere that I have to lift my pencil if I were drawing this. So the first one that I find is at x is equal to 0. I'm going to circle it so we know what we're talking about. This is the first discontinuity. So I'm going to scroll down and enter that in number 2. At x equals 0 is our first one. The second one that we come to, again, as we look at the graph, moving from left to right, is that x is equal to 1. I'm going to enter that into number 2. Scrolling back up to look at the graph, the next continuity that we have is that x is equal to 2. There's a hole. I'm going to add that to number 2. I'm going to go back to the graph. And we have another discontinuity at x is equal to 4. And again, I'm going to enter that in number 2. So now we've identified each place that has a discontinuity, each x value. So now we're going to fill in a chart for number 2 for each of these discontinuities. So I'm going to start by looking at x equals 0. The first thing I'm going to look at is what is the function value at 0. So I scroll back up, I can look at the graph or I can use the equation. The function value at 0 is our solid dot that we have when x is 0 that I've now colored in red. And so the function value at 0 is 0. Next question is, well, what's the limit as x approaches c from the left? So I'm looking from the left. So I'm following this curve from the left, and the limit as x approaches 0 is trying to be -1. Now I'm going to look at the limit as x approaches 0 from the right. So from the right of 0, I'm coming down towards that solid dot, and that value is 0. The next question is, well then, what's the limit as x approaches 0? Well, the left-hand limit and the right-hand limit are two different numbers, which means the limit at x is 0 does not exist. And if you want to write DNE, I will be fine with that. So, answering the last question, does the function value equal the limit value? Well, if the limit value doesn't exist, then obviously these two things cannot be equal, so no. Moving on to the next discontinuity is that x is equal to 0. Excuse me, x is equal to 1. So looking at x is equal to 1, the first thing I need to know is what is f of 1? Again, I'm looking for the solid dot. So when x is 1, I've just colored it in blue, the solid dot, which means the function value is 1. Next, I need the limit as x approaches 1 from the left. So from the left, the limit is trying to become 2. From the right, I'm trying to find the limit as x approaches 1 from the right. The limit value is trying to become 2. So now I need to answer the question about what is the limit. The limit as x approaches 1 of this function is 2, but the left-hand side and the right-hand side of the limits are trying to approach the same value. The last question, does the function value equal the limit value? Well, the function value is 1, the limit value is 2, so the answer to that question is no. Our next discontinuity is that x is equal to 2. First thing that I need to find is the function value at 2. So when I look at the function value at 2, I don't see any solid dots on the graph. So if I'm going to come back and look at the piecewise function, and when I look in this green box in the domain of my piecewise function, there's no place where x is equal to 2. So that tells me for sure that there is no value of the function when x is 2. So the function value does not exist. And again, we can write does not exist or DNE. Let's start looking at the limits. So the limit as x approaches 2 from the left is trying to be 0. The limit as x approaches 2 from the right is trying to be 0. So the limit of this function as x is approaching 2 is 0. The left-hand limit and the right-hand limit are the same. Does the function value equal the limit value? Well, the function value does not exist, so they cannot be equal. Next discontinuity is x is equal to 4. So looking back at the graph, the function value at 4, well, I have an asymptote it looks like. So when I come back over to my piecewise function, what I've circled in black says x cannot be equal to 4. So there is no function value. So that does not exist. Now we're going to look at the limits. The left-hand limit. As x approaches 4 from the left, the limit doesn't exist, but it's trying to approach -1. So it does not exist. However, it is approaching, sorry, not -1, negative infinity. From the other side, we're now looking at the limit as x approaches 4 from the right. Again, that one does not exist. It's approaching positive infinity, which means the limit as x approaches 4 for this function does not exist, and it's not approaching a single one of the infinities. It's not approaching positive infinity or negative infinity. Sorry. So does the function value at 4 equal the limit value at 4? They both don't exist, but two things that don't exist cannot be equal to each other. I think I'm teaching philosophy. So no, these two things are not equal. Moving on to number 3. Now consider the function f at a point where f is continuous. For example, x equals 3. I'm just going to look back at the graph real fast. At x equals 3, are we continuous? It appears to be a solid dot. Both sides are connected. I could draw the curve through 3 without lifting up my pencil. So I'm confident that the function is continuous at 3. So let's answer these questions. The function value at 3, looking back at the graph, the function value at 3 is 0. The limit value from the left and from the right, looking back at the graph. So coming from the left, the green that I've already drawn in is trying to go to 0. And then coming from the right, the red I'm drawing in is trying to be 0. So the limit as x approaches 3 of f is 0. And does the function value equal the limit value? And they do. They're both 0. So yes. Here's the definition of continuity. Please memorize this definition word for word. Anytime you are asked anything about continuity, something is continuous somewhere, in this class, any calculus class you take, you must reference this 3-part definition. If something is continuous, you must prove all 3 parts are true. If you're trying to say something is not continuous, you must show what part or parts of this definition are not true. So the function is continuous at x equals c if and only if all 3 of the following conditions are met. F of c must exist, must be a value. It can't be approaching infinity, and it can't be an open circle. The limit as x approaches c must exist. I'm going to specify that. For this part of the definition, for a limit to exist, specifically what that means is the limit as x approaches c from the left must be equal to the limit as x approaches c from the right. That is how you show a limit exists. That is the only way that you can show a limit exists graphically. And typically in this class, I want to see the left-hand limit, the right-hand limit, and then you can tell me what the actual limit is. Finally, in our 3-part definition, the limit of the function as x approaches c must be actually equal to the function value at c. So what I'd like for you to do right now is I would like for you to read the rest of the text on this page. So go ahead and hit pause so that you may do that. We are now going to go into some practice. Sorry, we should talk about these categories. Polynomial functions, some are, well, everything that's just a polynomial that's not a rational, so like your x squareds, your x cubes, your x to the fourth, all of those are going to be continuous. Your rational functions are going to have discontinuities, and your discontinuities for your rationals are typically where you have a 0 in the denominator, or division by 0. Your exponentials, those don't have any discontinuities. You can draw those without picking up your pencil. Same with your logarithmic. Those are inverses of each other. Your radical, those typically don't have discontinuities. They'll have restricted domains, but they don't have a discontinuity. Absolute value by itself doesn't have a discontinuity. If you are involving a rational now with an absolute value, then yes, you can. The greatest integer function, which we don't really talk about much, is a version of this, the step function, something to that effect. So that's riddled with discontinuities at each integer. Your trigonometric functions, your sine and cosine are going to be continuous, but your tangent is not. That's the one that's got the repeating kind of x cubed looking curve and then an asymptote. So there's a discontinuity throughout the tangent function. So let's look at the practice. So we're not going to touch calculator here. We just want to know if we have any points of discontinuity and then describe them as a jump, infinite, or removable. So your removable, that's going to be where you just have a hole in the graph, something like that. That's usually when we have something where you can factor the denominator out. Your infinite, this is where you have an asymptote, a vertical asymptote. And then your jump discontinuity is where you have to lift your pencil and move. So your jump discontinuity is something to the effect of this, where at an x value, you literally have to jump, lift your pencil to continue drawing. So looking at number 1 on our practice, we have a rational. We have something in our denominator, so we're looking for where we have division by 0. So we have a problem. The discontinuity is that x is equal to 2, excuse me. That's going to give me a 0 in the denominator. That means I can't make that go away. I can't factor the top and bottom, which means this is an infinite discontinuity because we have a vertical asymptote at x is equal to 2. So what part of our definition is having a problem here with our continuity? And the problem is that f of c does not exist. Number 2, we now have a rational, and I'm probably going to look to factor the denominator so that I can see if I can simplify this fraction. So I have an x plus 1 on top. When I factor the denominator, I have x minus 3 times x minus 1, which means I can't factor anything. I mean, I can't simplify this fraction at all, which means I now have 2 infinite discontinuities. I have one at x equals 3, giving me division by 0, and at x is equal to 1. They are both infinite. And again, that means my function value does not exist, and that is the part of the 3-part definition for continuity that I don't meet. Number 3, again, I've got these 2 polynomials. I have a rational, which means I'm going to look to see if I can simplify this fraction. I do need to know how to factor that top, x cubed minus 1. You can either remember the rule or you can use division to figure out the rule. Some way you have to deal with factoring your difference and sums of cubes. This one factors into x minus 1 times x squared plus x plus 1. Your denominator is a difference of squares, so we have x plus 1, x minus 1. At which point we now have 2 discontinuities. The x minus 1s, I have an x minus 1 on the top, and I have an x minus 1 on the bottom. That's just a special form of the number 1, so that can simplify my fraction. And that leaves me with this. So the discontinuity at x is equal to -1 That one is an infinite discontinuity. So again, f of c does not exist there. Now for the other discontinuity, that happens over here with this x plus 3 in the denominator, with the x minus 1 in the denominator. I'm underlining the wrong thing. I could simplify that out so I don't have an infinite asymptote there, an infinite discontinuity. So at x is equal to positive 1, what I have is a removable discontinuity, which means a hole, which again means f of c does not exist. Number 4, we have an absolute value. An absolute value graph is just a V. This one happens to be shifted to the right 1 from the origin, and I have no problems with that one. So there are no discontinuities with this. The next one, I have cosine x over x. I can't simplify this fraction and get that x out, which means the discontinuity is going to happen at x is equal to 0 because I have 0 in the denominator, which means that is an infinite discontinuity. And again, we're back to f of c does not exist. Number 6 is a radical. So we just have a square root, which means we've got a restricted domain, but there are no discontinuities with this. And in number 3, we have a cubic, and in a cube root, I apologize, there are no discontinuities. Moving on to the next page, we have an example. We have this piecewise function that we need to graph, and in number 1 it tells us we need to graph it where k is equal to 1. So what we're going to graph on this grid is actually going to be x plus 1 when x is less than 2, and we are also going to graph x minus 5 squared when x is greater than or equal to 2. So we have this piecewise function. First I need to put some axes in. So I'll draw in some axes. And I'm going to go ahead and start with the blue x plus 1. So that's a line. The y-intercept is 1. The slope is 1. And I'm going to go up until I get to 2. I'm going to have an open circle there because I don't have an equal sign with my less than symbol. There's no equal sign, which means I'm not ever going to be equal to 2 and using this part of the function. So I have a line for the remainder. Put an arrow on this end because it will continue on forever in that direction. In red, I have a parabola. My parabola has got a shift in it. It has been shifted to the right 5 units, so I move to the right 5. That's going to be the vertex of my parabola, so now I just draw my parabola over 1 up 1, over 2 up 4. Do the same thing to the left, over 1 up 1, over 2 up 4. And then I do have an equal sign with my 2 over here, so when I go to the left 3, I'm going to go up 9. Oops, went off my grid. And this is what my parabola is going to look like. Now I do need an arrow on the right side. It's going to continue on, but the left side is going to stop at 2. So here is my piecewise function. Number 2, use a definition of continuity to explain formally what must be true in order for f to be continuous at 2. So first and foremost, first piece of information, we must have that f of 2 exists. In this case it does. F of 2 is equal to 9. The next thing we have to have is the limit as x approaches 2 of f of x must exist. I'm going to specify, that means the left-hand limit and the right-hand limit must be equal to each other. And finally, the third part of this definition is that f of 2, must be equal to that limit as x approaches 2 of the function. Number 3, you'll see this question. On the test. This is a typical AP style question. Number 3, find k that makes f continuous at x is equal to 2. So when I look at my graph, this is not a continuous function because my blue line doesn't actually connect with my red parabola. So what we need to do is we need to figure out, well, what does k need to be so that that happens? So what I need to do is I need to make sure the two pieces, I need to make sure that the blue x plus 1, that is going to actually touch the red parabola, and I get to pick the k to make that happen. But I don't want to have that to happen everywhere. I want those two things to be equal when x is equal to 2. So that's what I'm going to work on. I want x plus 1 to be equal to k times x minus 5 squared, and I want this to happen only at one spot, and that's at x is equal to 2. So I'm going to replace all my x's with 2's. That way I only have one variable. I'm searching for k. So I'm going to have 2 plus 1 is equal to k times 2 minus 5. When I simplify that, I'm going to get 3 is equal to 9k, I believe, which means k is 3 over 9, which is 1/3. So if I use k as 1/3 in my piecewise function, my blue line and my red parabola should touch when x is equal to 2, making the function continuous. So this is a little bit of a limits review. And I think you've addressed all of these style limits in your past math classes. So we're going to go ahead and start with that first example, and we find the limit as x approaches pi. The first response whenever you see a limit is to try to substitute in, and if you don't get division by 0 or the square root of a negative number, you're happy, move on, you've got it. So we're going to go ahead and plug this in, and we get pi times cosine of pi. And we need to actually know what cosine of pi is, and cosine of pi, I believe, is -1. Give me a second. Yeah. So I have pi times -1, which is -pi. So the limit is just -pi simply from plugging in. In the second example, if I go ahead and plug in a 3 in the denominator, I'm going to get a 0. That's a problem. And so what I need to do is I'm going to try and factor. So let's see if I can rewrite it and remove the discontinuity. So I factor the top as a difference of squares, x plus 3, x minus 3. The denominator is x minus 3, and I look for silly versions of the number 1. I have an x minus 3 on the top and an x minus 3 on the bottom. That's a silly version of the number 1. I don't need to write that down anymore, so now I just have the limit as x approaches 3 of x plus 3, which is going to be 6. So there was a discontinuity in that second one at x is equal to 3, but it was a removable discontinuity. So here's the practice. What I'd like you to do is go ahead and work on some of these, and I want you to hit pause so that you pause the video so that you're working on these problems right here. And what I'm going to do is I'm going to put all my work on my paper, and then when you hit play again, you'll get to see all of the work and all of the answers. So give it a go on these, and when you're finished, hit play again. Okay. All of the answers with the work are on there. If you look at number 4, the numerator and the denominator are the same, which means it's approaching 1. I didn't write any work down for that one. Go ahead and stop the video. There is no more after this, but stop the video and make sure you have all your work and your answers correct. Have a nice evening.